Welcome to our Quantum Deep Dive. Today we're plunging into a really groundbreaking area. It's right at the intersection of artificial intelligence and quantum computing. And it's all inspired by some, really insightful work from Jurgo Schneppat titled Quantum Kernel Method in Hybriding Modeling. Our mission today, essentially, is to unpack how these quantum kernel methods are becoming, this essential bridge, connecting the machine learning we know with the, let's say, mind-bending possibilities of quantum mechanics. Think of it as getting a real cutting-edge understanding of one of tech's most exciting frontiers, tailored just for you.
Yeah, and what's truly fascinating here, what Schneppat's work really digs into, is that core question. Can quantum computing actually give us a significant practical edge in machine learning? Especially, and this is key, when you combine it smartly with classical methods. Not trying to replace everything, but finding that synergy.
Absolutely, that synergy. So let's navigate this. We're going to cover the core ideas, look at how these hybrid systems actually function, maybe touch on some real-world applications where they might really make a difference, and then, tackle the big challenges and what the future might hold. Okay, so first things first. Why even bring quantum computers into the machine learning picture? I mean, classical computers are pretty amazing, right?
They are, but they're starting to bump up against fundamental limits, especially with problems where the complexity just explodes, grows exponentially.
Right.
And that's precisely where this whole conversation around quantum machine learning, QML, gets really interesting. It kind of emerges as this promising interface using quantum mechanics to potentially, push past those classical walls that Schneppat discusses.
And within QML, one approach that seems really promising is quantum kernel methods. They feel quite pragmatic, taking quantum principles and plugging them into established, effective classical techniques. It's not this rip and replace idea. It's more like an enhancement.
Exactly. And this hybrid approach, it's absolutely critical right now because the current quantum machines, these NISQ devices, Noisy Intermediate Scale Quantum they aren't quite powerful or stable enough yet to run big, complex algorithms all on their own. Their real strength, for now, lies in doing specific things really well, like representing data in these incredibly high-dimensional feature spaces, something classical computers really struggle with.
Okay.
And then you hand that representation over to classical algorithms for the optimization part. It's a clever division of labor, really.
So for you listening, what we're really talking about here is a practical strategy, getting the best performance by, mixing and matching the strengths of both classical and quantum computing.
And this offers some pretty profound potential advantages for machine learning. First, there's this extended feature representation. Imagine trying to see a complex pattern in just a flat 2D drawing. Now, what if you could project that into some vast multidimensional space? Suddenly, the pattern might become really obvious, linear even. Quantum computers can do that mapping.
So it's like giving the machine learning algorithm a much bigger, more detailed map to work with.
Precisely. A richer space. Second, efficient kernel functions. Classical kernel methods are powerful, no doubt, but they can get computationally very heavy as the data gets complex. What Schneppat points out, and this is key, is that quantum computers could potentially calculate these complex kernel values much faster, like in polynomial time instead of the exponential time that might be needed classically for certain kernels. That's a huge potential speed up.
Wow, okay. Polynomial versus exponential is a big deal.
It really is. And finally, integration. These hybrid models, they're designed to slot into existing machine learning workflows. You don't have to completely rebuild everything, which is crucial for adoption.
Right, makes sense.
So all this together, it opens up completely new paths for things like classification, regression, pattern recognition, especially for problems that are just, too tough or too costly for today's classical methods alone.
Okay, to really get our heads around how these quantum kernels actually work their magic, we probably need a quick refresher on the quantum mechanics basics, right? The superpowers involved.
Definitely. Think about the most basic unit of information. Classically, it's a bit. Simple. Either a 0 or a 1.
Yeah.
But the quantum version, the qubit, it's much more interesting.
Right, because a qubit can be 0, it can be 1, or, thanks to superposition, it can be kind of a mix of both at the same time. It's not just one or the other until you measure it.
Exactly. It exists in this blend of possibilities, and that means a set of qubits can explore many possibilities simultaneously, offering a kind of inherent parallelism. Then you have entanglement. This is where it gets really counterintuitive, but also incredibly powerful.
Yeah, that's the one where two qubits become linked, right? Measure one, and you instantly know the state of the other, even if it's miles away. Spooky action at a distance, Einstein called it.
He did. And this property is vital. It lets quantum algorithms model really complex correlations within data extremely efficiently, things classical systems struggle to capture.
Okay, so superposition for parallel exploration, entanglement for correlations. What's the third one?
Quantum interference.
Like waves adding up or canceling out.
Precisely like waves.
Okay.
Quantum algorithms are cleverly designed so that the computational paths leading to the right answer interfere constructively. They reinforce each other. While the paths leading to wrong answers interfere destructively, they cancel out. It helps amplify the correct solution. Grover's search algorithm is a famous example that uses this.
Okay, so superposition, entanglement, interference, these are the building blocks. And they're manipulated using quantum gates, things like Hadamard, Pauli, C&OT gates.
Yeah, those are the tools.
Within these gate-based quantum computers, like the ones IBM Q and Google Sycamore are building. And those are the systems relevant for these kernel methods.
Exactly. Those gate-based systems provide the flexibility needed to build the specific quantum circuits that calculate these kernels.
Right. Now let's connect these quantum superpowers, these principles, directly to machine learning, specifically through these kernel methods.
Okay, so in classical ML, kernel methods are frankly ingenious. They let you tackle nonlinear problems where your data isn't easily separable by a straight line, digamos. But instead of explicitly doing some complex, maybe computationally expensive transformation into a higher dimension where it is separable, you use a shortcut, a kernel function, KXX. It cleverly calculates the similarity, the dot product, between two data points as if they were in that higher space without actually going there.
So you get the power of higher dimensions without the full computational cost. Like support vector machines, SVMs, they use these all the time, right? Polynomial kernels, RDF kernels.
Exactly. Which brings us to the crucial step Schneppat focuses on. How do quantum kernel methods improve on this? Well, they use a quantum computer to actually calculate that kernel function.
Oh, okay. And how does that work? It's not just classical math anymore.
No. What you do is you encode your input data point, say X, into a specific quantum state. We write it as wrangle using a carefully designed quantum circuit. Then the quantum kernel value, KQX, between two data points X and X, is found by measuring the overlap, essentially how similar those two quantum states wrangle are.
Okay, so the quantum computer prepares these states and measures their similarity.
Exactly. And that measurement can, in theory, be done efficiently on a quantum computer. The potential advantages here are really significant. First, these quantum states live in what are called Hilbert spaces. Think of these just incredibly vast, abstract spaces with potentially exponentially more dimensions than classical computers can realistically handle. This could allow for finding much more intricate patterns.
So it feels like it's not just doing the same thing faster. It's potentially seeing patterns that are just fundamentally invisible to classical methods because they can't access that kind of complexity. A shortcut to deeper insights.
That's the hope, yes. That's the theoretical promise. But, connecting this back to reality, while the theory is compelling, there are practical hurdles.
Right.
We have to deal with the noise in today's quantum computers, which affects the accuracy. Encoding classical data into these quantum states isn't trivial either. And crucially, we always need to compare performance against the very best classical methods, like, say, deep learning, which are also constantly improving.
Which leads us nicely into the practical side. Hybrid quantum AI models, because as you said, the NISQ devices aren't perfect yet, so combining seems like the smart play, as Schneppat emphasizes.
Absolutely, the way to go right now. You let the robust, scalable classical algorithms handle the bulk of the work, data prep, maybe the main optimization loop, making final decisions. Then you strategically bring in the quantum computer just for those specific, really hard computational steps where it offers a unique advantage, like calculating these complex quantum kernel values.
So it's like having this specialized super tool, the quantum processor, that you use only for the trickiest subproblems within a bigger, more standard workflow.
Precisely. A typical hybrid setup, like Schneppat describes, might look like this. You have an input layer preparing the classical data. Then a quantum kernel layer where the quantum magic happens, generating that KQX from the quantum states.
Okay.
Then that kernel information feeds into a classical ML layer. This could be an SVM or even part of a neural network, using those quantum computed similarities for training and making predictions.
And then presumably some classical optimization to tune the whole thing.
Exactly. Classical optimization and evaluation wrap around the whole process to fine-tune it.
So, drilling down a bit, how exactly does the classical algorithm benefit from this quantum boost? What does it get?
Primarily, it gets that enhanced feature representation we talked about. By implicitly working in those huge quantum Hilbert spaces, the classical algorithm might find it much easier to separate complex data. It also benefits from the potentially efficient calculation of similarities between data points, especially if those similarities involve really complex, high-dimensional patterns that would be very costly to compute classically.
Right.
And for certain specific types of problems, this could theoretically translate into that potential for exponential speedup, though proving that in practice is still ongoing research.
And this isn't just theory on a blackboard. People are actually building and testing these, right?
Oh, yes. Schnapp mentioned some key examples, like Havlicek and his team back in 2019. They actually showed on IBM's quantum hardware that quantum kernels could separate certain complex datasets better than classical methods, albeit for small datasets at that time.
Okay, early proof of concept.
Exactly. Then Schuld and colleagues, also in 2019, provided important theoretical backing, showing mathematically how quantum kernels could offer better separability. And more recently, like in 2021, Google AI Quantum ran benchmarks comparing quantum kernels against deep learning, finding specific cases where the quantum approach actually showed an edge.
So if you're listening to this, what does it mean for the real world? Where might we actually see these hybrid models pop up and make a difference down the line?
Well, think about fields struggling with massive complex data where subtle patterns are key. Pattern recognition and classification is a big one. Think advanced image or speech recognition, maybe even spotting really sophisticated fraud in financial transactions. Also, optimization problems in financial modeling. Things like managing complex investment portfolios, assessing intricate market risks, or maybe optimizing vast dynamic supply chains. Anywhere that finding patterns in market data efficiently is critical.
Makes sense.
And definitely biomedical applications. This is a really exciting area. Using these methods for drug discovery by analyzing molecular structures, maybe analyzing genomes for disease risk prediction, or enabling truly personalized medicine based on complex patterns in individual patient data.
Wow. The potential seems enormous, especially, like you said, for problems swimming in high-dimensional data. Now, okay, this all sounds incredibly exciting, but let's be realistic. It can't be smooth sailing. What are the major roadblocks? What are the big challenges facing quantum kernel methods and these hybrid models today?
You're right. There are definitely significant hurdles. The biggest ones right now are technological, really centered on the limitations of current quantum hardware, these NISQ devices. First and foremost, error rates and noise. Quantum states are incredibly delicate. Environmental factors cause decoherence, meaning superposition, and entanglement, just decay. Plus, the quantum gates used to manipulate qubits aren't perfect, they introduce errors. All this impacts the precision of the calculations.
So the fantastic theoretical ideas kind of run into the messy reality of building and controlling these quantum systems.
That's a good way to put it. And tied to that are hardware limitations and scalability. We're still working with a relatively small number of qubits, and how well they're connected matters a lot too. People are developing error correction techniques, but these currently require a huge number of physical qubits just to create one stable, reliable, logical qubit. It's a massive overhead and a big scaling challenge.
Okay, so hardware is a major factor. What about challenges on the theoretical side? Like, how do we even know for sure if quantum is providing a real advantage?
That's a really crucial and difficult question. How do we definitively characterize and prove a genuine quantum advantage? It's tricky. For some problems where quantum algorithms look promising, clever classical algorithms might emerge that can approximate the result efficiently anyway. And many of the theoretical proofs of quantum speedup are based on fairly abstract mathematical problems that aren't always directly mappable to the messy real-world applications we care about most.
And this whole comparison gets even more complicated because classical AI isn't just sitting still, right? Deep learning and other methods are evolving incredibly fast.
Exactly. That's a critical point. When we compare quantum kernel methods, we absolutely must benchmark them against the very best state-of-the-art classical techniques. That means sophisticated deep neural networks, maybe transformer models, highly optimized classical kernel methods running on powerful GPUs.
It has to be a fair fight against the reigning champ, not just against simpler methods.
Precisely. Future research really needs to focus on these rigorous, fair comparisons to pinpoint where quantum kernels offer a clear, demonstrable advantage over the best classical tools we have.
Okay, so lots of challenges. But despite all that, the potential is still massive, and the field is moving fast. What advancements are on the horizon? What gives us hope these hurdles can be overcome?
Well, there's significant progress being made on the quantum hardware front. People are working intensely on building more stable, fault-tolerant quantum computers and improving those crucial error correction codes. And on the algorithm side, researchers are constantly developing new approaches, things like variational quantum algorithms, more sophisticated hybrid quantum classical circuits, all designed to get the most out of near-term hardware and boost performance.
And if these breakthroughs happen, where could they lead? What are the potential killer apps?
We could genuinely see these models transform fields, like biotechnology, enabling detailed analysis of molecular structures for drug discovery like never before. Finance could be revolutionized by hyper-complex risk models and predictive algorithms. And think about materials science and chemistry being able to accurately simulate quantum interactions could lead to the design of entirely new materials with amazing properties. Industries like pharma, financial services, logistics, advanced manufacturing, they're likely watching this space very closely.
So, connecting it all back, it really feels like while the full dream of fault-tolerant quantum computing is still a way off, these hybrid models are the essential practical bridge. They're making quantum computing potentially useful now. All right, so as we bring this deep dive to a close, let's crystallize the key takeaways. If you remember just a few things about quantum kernel methods in hybrid models, what should they be?
Okay, first, the core idea is that they theoretically offer an advantage by working in these incredibly vast quantum Hilbert spaces. This allows them, potentially, to find and separate complex data patterns more effectively than classical methods can alone. Second takeaway, hybrid models are absolutely critical today. They cleverly combine quantum's power for specific hard calculations with the robustness and scalability of classical algorithms for the rest of the pipeline.
Right, best of both worlds.
Exactly. And third, the potential application areas are really broad and impactful, ranging from better pattern recognition and financial modeling all the way to drug discovery and personalized medicine.
But, and this is a big but, we have to remember the significant hurdles. Technological challenges like noise, errors, and scaling the hardware are very real. Theoretical challenges improving a definitive advantage remain. Widespread industrial use is still limited by these factors. The next few years, honestly, are going to be crucial for validating whether these methods truly live up to their potential against ever-improving classical AI.
Yeah, the future of machine learning could be fundamentally reshaped by these quantum-assisted approaches, especially for those really complex classification and optimization tasks that push classical limits.
What stands out to me, thinking ahead, is this fascinating race. Will quantum kernels definitively prove superior to advanced deep learning for certain key problems? Or will classical hardware and algorithms continue to advance so rapidly that they keep pace, or even solve the noise and scaling issues faster? It's really unclear right now.
And that uncertainty, that ultimate question of whether quantum computers will become large-scale and reliable enough to truly surpass classical systems across the board, that's what makes this field so incredibly exciting. Regardless of how it plays out, the interplay between quantum computing and artificial intelligence is undeniably one of the most dynamic and important research frontiers of our time.
Absolutely. Well, we've really only scratched the surface today of the insights in Yorgo Schneppat's work. We definitely encourage you to explore more about his research in this whole fascinating area. Thank you so much for joining us on this quantum deep dive. You can find more information about Yorgo Schneppat's work at schneppat.de. Until next time.